on what is, in fact, our last topic in Engineering 216. Whew. That motion is getting to me. Now, I know that there are a few folks here that are in another world right now, given the experience you're about to have in an hour and a half, but we will make it through it during our last topic. So the at-home spreadsheet, I've sent that via email. You all have that. The bonus homework is open. We were just talking about course evals right before class opens. In all seriousness, I do genuinely review that feedback, and if there's some actionable stuff that you think could improve the class, I'll act upon it if I can. So if you have any of that feedback, I really would appreciate it. If you upload proof that you did it, I don't want to see what you wrote, just upload proof that you did it, I'll add 10 points to your homework average. So, yeah, that can bump your grade up a little bit here in the end. On the homework schedule, everything's graded now. We're actually up to date. Homework 8.3 is due Friday at 5 p.m. I imagine if I had made that due this morning, some of you would have hated me anyways. I didn't know about the celebration after this class, so this was a bit serendipitous. We'll have it due Friday at 5 p.m. I did post a little video to do a clarification on the second problem. I think, honestly, what my intention for the problem was versus the way that it's worded in the textbook was a little different. So the video that I posted hopefully clarifies that. Homework 9 is due on Thursday, April 21st. That's next Thursday. I'm not going to take late submissions on that one because I'm putting the solution up right as that goes live. So when we meet Thursday, April 21st, you'll have the solution to homework 9. That'll be the solutions for all the homework assignments in the class. And we are canceling class on Tuesday. I'm not going to do a pre-recorded lecture. I'm just canceling it. If I do pre-record anything, the only thing I'll pre-record is finishing out some examples that we might not get to today. Because I have 2 buckling examples I'd like to talk about today, and I'm at least going to get through one of them. The second one I might trail over for a few minutes, and I'll just post that as sort of an add-on. But we will not have a lecture on Tuesday that you need to make up. Sound good? All right. Before we get into this topic, I'm curious, does anybody have a ruler, like not a scale, but a ruler? Does anybody have a ruler? I'm just curious. It's a ruler. Do you have one?
I do. I don't think I have it right now.
That's okay. That's okay. It's all right. Perfect. That'll be good enough. Okay. All right. I want to talk about buckling. Now, this is our last topic of the semester, and this will be good enough to sort of explain the point. I'm not lying to you, but I've glossed over something throughout the entire semester that we need to correct today, okay? And that is that we have assumed that elements in compression and elements in tension behave the same way. And in some instances, that's true. In many instances, that is really not true. Okay, now I have here this 45, 45, 90 triangle, but it could be a yardstick, it could be a ruler, just doesn't really matter. Okay, but I want you to imagine that you had like a yardstick or a ruler or something like that in your hand. And take that ruler or yardstick and yank on it. Okay, I'm sitting here pulling on this, and I can pull it all day long, and I'm not going to be able to rip this thing apart. I'm not that strong. But now imagine taking it and applying compression. Okay, now this is actually a little stiffer than your garden variety ruler that you get at Walmart, but you find something a little different when things are subjected to compression, and that is they sort of have this tendency to bow out, right? You take the yardstick and you apply it in compression, and it goes, and then it suddenly bows out. That is a particular phenomenon in the land of stress analysis called buckling. And to give you some numbers to kind of wrap your head around how important this is, okay, if I take a garden variety yardstick, wooden yardstick from Lowe's or wherever, and I take that and I yank on it in tension, I could probably put a few hundred pounds on it before it starts to fracture. But if I press on it in compression, it'll probably fail at like 6 pounds, okay? It is much lower, it has a much lower capacity in compression because when you subject things to compression, you start to enter the realm of experiencing what are called stability failures. Things in compression like to buckle. And when things buckle, it results in a sudden loss of stiffness, and the column suddenly goes. Now, what I want to do today is I want to talk about how buckling works. Now, I'm going to warn you, actually, let me go back to my previous slide. I do have some calculus and some diffie-q approaching, but I'm not going to make you do that. I'm just going to make you watch and absorb. But don't worry, we're not going to have to solve any differential equations to handle buckling problems, at least for the types of buckling problems that we're going to deal with in here. In the end, we are going to yield a very nice, pretty plug-and-chug expression at the end of the day. I will go ahead and tell you my notation here in the slides is a little different than the book, but I kind of think this notation is a little bit easier to follow. Okay, now I want to talk about buckling from the perspective of a straightforward, simple column. So I'm talking about a column that's simply supported, so we'll say it's pinned or rollers on either end, whichever way you want to think about it. But ultimately, when I say simply supported for this column, I'm talking about a column that is allowed, where the ends are allowed to rotate, but they're not allowed to translate this way. Okay, so the ends rotate, but they don't translate. And I want to determine what is this magical load P that this to this. How does it suddenly go into this buckled state? And so what I'm going to do is I'm going to use a little bit of moment curvature, okay? So moment curvature is my familiar differential equation. The second derivative of deflection is m over EI. But we're going to also break out my secret weapon, which is the same be a sci-fi fan, and I'm going to cut a section through some X in the structure and look at the internal equilibrium and sum moments. So if I sum moments, I get the internal moment acting one way, and then in addition to that, I have the axial force multiplied by a moment arm, and the moment arm is how far away we are from the original shape. So I can relate the internal moment inside the column to the applied axial load and how much it's deforming. That's what this Y is, how much it's bowing in and out. And so I can substitute that into our differential equation. So instead of derivative is m over EI, I can say the second derivative is this negative Py over EI, and I get this. This is a second order differential equation, okay? Now, let me solve this equation. So the first thing that we're going to do, we're going to take this P over EI, we're going to make up a term, we're going to call it alpha squared. The reason why I want to call it alpha squared is because I have a second derivative here, I want a squared term there. Now, at this point, I have a second order differential equation that I need to solve, okay? Let me show you, I think what I am, I don't think I'm stretching to say, I think this is an engineer student's favorite method to solve a differential equation. So, y double prime, let's see, a squared times y equals 0. You've never used this before, have you?
Every day.
Yeah, that's what I thought, yeah. So this is a very common differential equation that you find in Math 335, and you find the solution right here. It's kind of hard to see, but it's C1 times the cosine plus C2 times the sine. For those of you that haven't had differential equations yet, the whole point of differential equations is we have an equation that states, in this case, we have an equation that states that we're looking for some function y, such that the second derivative of that function plus alpha squared times that function equals 0. Okay? And so the whole point of Math 335 is to figure out what are those functions that meet that requirement, that satisfy that equation. Okay? And so what you find when you take differential equations is that a lot of times your solutions are either exponentials, like e to some function or some quantity times x, or they're sines and cosines. And I don't think that's a big stretch to try and wrap your head around, right? So we have an equation here that says the second derivative of the function plus a polydjunct times that function equals 0. And I'm thinking, okay, second derivatives, okay? What's the derivative of the sine? It's the cosine. What's the derivative of that? The negative sine. So trig functions have a way of repeating their derivatives a fair amount, right? So I think it stands to reason that having a trig function in our solution, a cosine and a sine function, is not that crazy. I mean, think, this is a function that's showing the deflection equals this. Well, what are cosine and sine functions but sinusoidal? It's not that crazy to think that the column is going to deflect in a sine wave type fashion. So that's the end of Math 335, right, for this class, is that Math 335 will teach you how to go from this to this. But like indefinite integrals, we have arbitrary constants we have to deal with, and this happens in differential equation solutions as well. We have y of x equals an arbitrary constant times a function, plus an arbitrary constant times another function. So how do we solve for those arbitrary constants? Well, we need boundary conditions, right? We need specific boundary conditions that relate to our problem. In other words, this is a general solution for this general type of differential equations. But I want to be able to in my problem, I need boundary conditions to deal with this. I need two boundary conditions because I have two arbitrary constants. Now, I propose that the boundary conditions are related to the deflection here and here, because I know that the deflection there is 0, okay? So specifically what I'm going to say is that this function has to equal 0 when x is 0 and when x is L, because this is the bottom of the column, this is the top of the column. 0, x equals 1, x equals 2, x equals 3, to x equals L. And so I've got two unknown constants, two boundary conditions, two equations, two unknowns. That should be something that we were pretty familiar with. So let's solve for these. Okay, so y of x equals c1 times the cosine plus c2 times the sine. Let's plug in the first one. Okay, so the first boundary condition, we plug in x equals 0. So y of 0 equals c1 times the cosine of 0. Cosine of 0 is 1. Sine of 0 is 0. Plug and chug, boom, we get that. Suddenly our problem got a lot simpler. Okay, so now what we have to do is we have to plug in x equals L, right? And so when we plug in x equals L, we get this. Interpret that, okay? If you're just running through the motions of math land, you might look at this and just sort of say that, oh, well, C2 is 0. But there's actually a lot. This is kind of a tricky problem to deal with, okay? I want to talk about trivial and non-trivial solutions. So let's ignore all of the math that we've just done, and let's look at this equation. So I have C2 times the sine of alpha L equals 0. What are the possible that this could be true? Well, C2 could be 0, right? That would work, right? That makes sense. Well, here's our function. This is the function for the deflection. If C2 is 0, that would be the buckled column that has no deflection. In other words, we would be looking at this column and saying that it's not buckled. But we know it is, right? So looking at this equation here and saying, well, one way it could be true is that if C2 is 0, yeah, that's true, but that's... Let me give you another one that's a little easier to interpret. 0. Would that satisfy this equation? Right? C2 times the sine of alpha times 0, that would be the sine of 0, which is 0. That would work, right? Mathematically solve this problem, but what would that mean? What if I... That's not a viable solution. What about alpha? Could alpha be 0 in that work? Yeah, but alpha is also a trivial solution because that would be... So, what do we do? Well, either A is 0 or B is 0. So what about the sine? What about looking at the sine function and seeing when that equals 0? Maybe that one's not so trivial. The sine function, it comes in waves, and the sine of x equals 0 whenever we have integer multiples of pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. So maybe this alpha L term needs to be an integer times pi, right? So I can solve for alpha, but wait a minute, didn't I already have an expression for my load? I think that's what I was after. Amount of force required to buckle the column. Boom. There are a couple obvious questions that come into play. That's great, but what's n? What do I use for n? Like, do I just make up something? Well, look at the expression. Okay, the expression utilizes n squared, so I'm only going to consider positive terms. I'm not going to consider n equals 0 because that would be another trivial solution. N equals 3. Well, what you can do is you expression for deflection, and you get these different shapes of the column as it's being buckled. We call these mode shapes. And what we find is that if we have like column would look like if it was braced, if it had bracing, at given points, this would be its capacity. But look what happens load side of things. We have n equals 1, we have a term. N equals 2, we have a term for the capacity. N equals 3, we have a term for the capacity. Think about this. If I have this column in front of me and I keep stacking force on it, which value am I going to hit first? I'm going to hit this one, right? Because this value is smaller. This column, this is the one I'm going to hit first. So the critical buckling load, or the elastic buckling load for a column, is this, with n equals 1. Okay, so pi squared EI over L squared. That is our basically fundamental expression for determining capacity. Load, we can use axial stress. And so what we would do is we would take this expression and we would divide it by the area. So if we take this and divide it by the area, we have this term here called I over A. And what we tend to do in engineering land is we tend to take that term I over A, we tend to rewrite it a little bit. We call it I over A, we call I over A R squared. Okay, and there's a value for that. We take I over A, we call it R squared. We can take the R squared and combine them a little bit. And what we get is this term L over R. L over R is what is called the column. So let me back up a second and explain what R is. So again, R is what we call the radius of gyration. It is just the square root of I over A. So first off, if you remember our ceiling. So we had axis 1, 1, we had the I, we had the S, and then I said there was this R value. And you're like, what's this? I said, don't worry, we'll get to it later. This is us getting into it later. All you do to compute R is you take I over A, take the square root. I over A, take the square root, and you'll get your R value. If you want to know, though, actionably what R is, all R is sort of a normalized version of the moment of inertia, but one of its benefits is that if you look at the units, R tends to be expressed in length, inches, millimeters, etc. If I take the length of the member and divide it by R, I get this term called slenderness, and slenderness is unitless, so it makes our life a little easier from a units perspective. So it's something to think about when you're looking at these computations. And dealing in slenderness makes our life a little easier. Okay, I'm going to stop for a sec before we move on. I want to see if any the math so far. And again, we haven't applied to some of these formulas yet, but I think you're going to find it's pretty straightforward. Good. All right. Now I want to this term called the effective length factor. This is presented a little differently than it is in your book, but I think this is a little easier to use. So let's talk about the effective length factor. What the effective length factor is doing is adjusting for boundary conditions. Okay, so that solution that I just derived, and I got I over L squared, that is a very valuable formula, but it assumes that the column is simply supported on top and bottom. What if it's not? What if it's fixed on the bottom and free on the top? Can I explain how? So what we have here is a pin-pin column, okay? Now I propose that this pin-pin factor to basically try and relate all of my other columns to this one. So here's the length of the column, okay? Let's talk about this fixed free column here. This is what it looks like when it buckles, okay? Imagine I took this deflected shape and sort of like extended it. See how this deflected shape here and this deflected shape here are basically the same? In other words, what I'm proposing is I can use the differential solution for this column, provided that instead of using a length of L, I use a length of 2L, so that the columns map 1 to 1. Does that make sense? All right. So what I'm going to do is I'm going to express that through what's called length factor. So for fixed free column of 2, okay? And so the idea is I have to take that length and multiply it by 2 so that its buckled effective length matches what that is for a pen-pen column. So the effective length factor for a pen-pen, that's the standard. Pen-pen is 1, fixed free is 2. Remaining other cross sections. All right, so this is fixed, this is fixed, pen, fixed, free. I'm going to give you all a sec to write this down. Oh, you all write that down. All right, so let's go ahead and look at a given example. We're going to do, I want to get through, but I want to try and get through both. If we can get through this one, we're going to be rocking and rolling, but if we can get through both, that'd be even better. I'm going to say it's a column with fixed ends, okay? For wood, value be 1600 KSI, and I'll determine what is the column's maximum permissible length if the allowable stress is 5 KSI, and what is the central load that the column can carry if it's 8 feet long. Now, before we get into this problem, I want to be crystal clear. 2x4s are not actually 2 inches by 4 inches. They're a little less, okay? We're going to use 2 inches by 4 inches for the purpose of this problem, but I just want everybody to know that a 2x4 is not 2 inches by 4 inches. It's 1.5 inches by 3.5. So, all right, everybody good? All right, let's get into our problem. Okay, so So we're going to do a couple things right off the bat. So the first thing I'm going to do is I'm going to compute some section properties. So we're given a B of 2 inches and an H of 4 inches. Okay? Now, we know that the area is BH. All right, that's easy. Now this is important. I'm going to do something. I'm going to say that I is this. And you're going, excuse me, what? Hold on for a sec. That's not the formula for the moment of inertia, Dr. Mike. The formula for a moment of inertia is BH cubed over 12. Why are you doing B cubed H over 12? Let me explain. Let's Let's take a little bit of a detour. Okay. Let's compute Ix. Ix is bh cubed over 12, which is 2 4 cubed over 12. What is that? Need some help on that.
Eight thirds, 26.
This one is?
Sorry, I squared it.
No. Yeah, I was going to say this one should be different. And that's inches to the fourth. Now let's compute Iy. And if you're wondering what am I talking about here, here's what I'm talking about. So there's a difference between the moment of inertia of this and the moment of inertia of this, where this is 2 inches and this is 4 inches. So if I wanted to compute the moment of inertia of this, it would be Ix, bh cubed over 12. But now I want to look at this. This is going to be my Iy, and this is going to be b cubed h over 12. In other words, the width is the 4 inches and the height is the 2 inches, and it's the 2 inches that I'm cubing. And so this is there we go. Okay, so here's my point. Why am I computing both? I am taking this and I am loading it in compression. It is going to buckle whichever way it's going to buckle, okay? And I propose that it is going to buckle about the axis that's easiest. Your axis, Ix, or it's Iy because the moment of inertia is smaller. So when I compute my R value that I'm using for design, Ry. And again, all R is just a normalized expression of the moment of inertia. That's all it is. So it comes out in inches. So what do we get for this?
Seven, eight.
Everybody good? Okay, so let's deal with part one. We'll call it part A. Okay. Now part A is asking basically the following. It's saying, what is L? Here, actually, let me erase that. If sigma allowable is 5 KSI. Okay. All right. 5 KSI, what is L? Okay. Well, I know that a column will buckle when its applied stress is pi squared E L over R squared. So that's when the column will buckle. Okay, so let's set that buckling stress equal to sigma allowable. Okay, let's see. Is there anything that we need in this equation? Well, we need E. Weren't we given E? I think E was sine. Well, we were told that the column has fixed ends. And if a column is fixed, what is K? I'm asking you.
I didn't get it right down.
You didn't, okay.
That's five.
There we go, 0.5, yeah. So we're going right there, yeah, so fix, K is 0.5. No, it's all right, it's all right. So K is 0.5, right? So we look at this expression and we go, well, gosh, like, what's left? We have E, we have K, we have R, we have sigma allowable, we need to solve for L. So let's do a little bit of right here. So KL over R squared is pi squared E over sigma allowable, right? Then I'm going to take the square root of both sides, and I'm going to get KL over R is the square root of pi squared E over sigma allowable. So L is R over K square root of. So R, now R we just got was 0.578 over K of 0.5. Now let's see what's going on in this square root. We have pi squared, 1600 KSI, and then we have 5 KSI. So inside the square root, what happens to the units? They cancel. And outside the square root, we're left with inches. Answer is going to be in inches. What is that going to be? It's like 64.9.
Yeah, but it runs up to 65.
Yeah. Or if we wanted to express that in feet, we could say, do that. Curious, is everybody okay with this? I mean, I'm hoping this is pretty simple, but it's not too challenging. See what part B is asking. So if we go to part B, what's part B saying? What central load can be carried if the column is 8 feet long? So that one's pretty simple, right? So part B. So what is P if L is 8 feet? Bless you. So again, this is pretty easy. So again, E is, so what we have? We have E is 1600 KSI. Since we're solving for loads, let's just use the I value. The I value was 2.67. We have K, again, is 0.5. L is 8 feet, which is 96 inches. I'm going to go ahead and tell you right now, it's usually a lot easier to just say KL is 48 inches. Just go ahead and do that now. I don't think it's a big deal, but I find it a little easier to go ahead and just multiply that out. Now, E critical, according to our buckling formula, is pi squared EI AL squared. And so just to make sure everybody has these expressions, what we're talking about is P critical is pi squared EI over KL squared, and sigma critical is pi squared E, and then it's KL over R squared. So formulas are similar, just one's giving you a load, one's giving you a stress. And so this is pi squared, 1500, 2.67 inches to the fourth. .48 inches squared. Don't forget to convert your KL to inches. And so what are we getting for this?
$18.29.
18.29 kips. Right? This is how much load the column can experience before it buckles. Now, I do want to do a little calculation off to the side. So that's P over A. So let's say I put 18.29 kips over a 2x4, which is 8 square inches. What is that? Has everybody brought their Casio FX115 ES Plus or similar scientific calculators? 2.28. Okay. All right. What was sigma allowable for the wood? You might remember, I think it was 5 KSI. Let's take a second and talk about that. Let me move my mouse pointer out of the way. So, what we're doing up here, where we have the P critical, pi squared E over KL squared, we're trying to figure out the load that will cause it to buckle, right? But then a follow-up question is, will it happen? See, I propose one of two things is going to happen. Either the column is in fact going to buckle, or it's sigma allowable load. And so how do you figure out which one governs? Well, it's a calculation. See, 18.29 kips is going to cause the column to buckle. And that stress is well below the allowable stress for the column. So in this instance, I'm going to say buckling governs. And we'll say that P max is 18.29 kips. Next problem is that might not happen. And with the next problem, we might find that, wait, we're actually governed by just the axial load. And it's easier to see that by just doing the problem, okay? All right. We got plenty of time to do this, so this is great. Let's go and see if this made sense. Everybody good? Okay. Let's do our next, and it's our last example problem. You know, you're gonna have me for another year, like another year of class. So we have a square bar. Okay, square bar. This square bar is to support a load of 20,000 pounds on a length of 10 feet. Okay, so if the ends of the column are pinned, we're going to determine the required, assuming sigma allowable is 10 KSI or assuming sigma allowable is 4 KSI. Okay, and we're going to find different results for the different parts of the problem for different reasons, okay? All right, so first I'll take care of some units. So P is 20 kips. Is 10 feet or 120 inches. Remember, my preferred units, kips and inches. So dealing in preferred units, that's already taken care of. This is already taken care of. This is already taken care of. Now, I have a statement here that says the ends of the column are pinned. What does that mean if the ends of the column are pinned? A is 1. And what's the rotational moment of inertia of this problem? For the folks that are focused on dynamics in here as opposed to formables. Joking, because I still got folks that are focused on 214. Okay. All right. Bar. So let's do some things with that square steel bar. All right. So we're talking about a bar that's B wide, B tall, right? So we know that the area is B squared, and we know the moment of inertia is BH cubed over 12 or B to the 4th over 12. So therefore, the radius of gyration, which is the square root of I over A, is the square root of B to the 4th over 12 times 1 over B squared, which is the square root of B squared over 12, or B over root 12. And you could probably say, isn't that 2 root 3? No, I'm just leaving it root 12. That's good enough. Okay. So now let's look at the column properties. Off to the side, because again, I think it's kind of easier to do some of this stuff in pieces. So again, K is 1.0. L was 120 inches, so therefore KL is also 120 inches. We are going to need probably KL squared, so we might as well go ahead and do that now. And so that's going to be 100 or 14,400. And we're also going to need KL over R squared. But actually, hold on. Let's take it one step at a time. Let's do KL over R. So KL over R is 120 inches divided by, what is it? B over the root of 12. Right? So that's going to be 120 root 12 over B, right? Just flip and multiply. So KL over R squared is going to be, what is it? 120 squared, square root of 12 squared over B squared. So that's 14,400 times 12 over B squared, which is, I think that's 172,800. over B squared. Notice how I was kind of being maybe a little fast and loose with the units in some of that algebra there, but I already converted everything in the beginning to where it was consistent. I already said kips and inches, so I think that's probably okay. Now, let's assume elastic behavior governs, or assume buckling governs. Okay, how do we want to do that? So we're trying to figure out, so let's see, we know P critical is pi squared EI over KL squared. That's what we know. Now, what do we know about this problem? Or what do we know about this? So, let's go here up top. We're going to determine the dimensions required to support a load of 20,000 pounds. So, in this instance, we know, okay, this is the expression that will cause the column to buckle. So, let's take P as 20 kips, solve for B. Now, how do we do that? Well, let's see. So we have P critical is pi squared EI over KL squared. So what do we got? Well, P is 20 kips equals, let's see. So we have pi squared. We have 1600 KSI. Wait, no, sorry. That's the other problem. 30,000 KSI. Again, was it b to the fourth over 12? So b to the fourth over 12. And what was KL squared? I thought KL squared was 14,400 inches squared. Is that right? So do we know everything but b? Yeah, we know everything but b. So 20, 12, that's going to equal b to the fourth. So if I take, I'm going to get b. Right? And you know in a calculator, to take the fourth root, we just raise it to the 1/4 power. So what do we get for that? Four, 6. 2.46. Also, square time. 1.84, like 848, something like that. Yeah, okay. All right. That, and this is where you want to pay attention, right? So this is telling me that if a column has inches, that the column will withstand buckling under a load of 20 kilos. Now, what we go off to the side is say, note. If B is 1.848 inches, what is sigma axial? It's P over A, which is 20 kips over B squared. What is that?
66.
5.86. Do I have a second on that? All right. Everybody got this? Okay. So let's make some sense of this problem and call it, because I know everybody's attention is diverted elsewhere this morning. All right. So part A. What is B if sigma allowable is 10 KSI? Okay. So if column is controlled by buckling, then B has to be greater than or equal to 1.848 inches. Is that a fair statement? Okay. If B is 1.848 inches, then sigma axial is 5.86 KSI. Oh, is that a fair sentence? So, is there a problem with B 1.848? In other words, B min is 1.848 inches. I say no. Because this is the required dimension of the column to a load of 20 kips. And if I use that dimension, my axial stress is not. But we're going to have a little bit of an issue with part B. So let's talk out part B. So part B. What is B if sigma allowable is 10 KSI? Well, I propose that if that's the case, oh, 4. Yeah, sorry. Let me do this. You're right, that's 4. That if we have 4 KSI, well, how do things change? Well, this statement is still true. If the column is greater than or equal to 1.848 inches. But if I were to use 1.848 inches, I have a problem. So here's what I'm getting at. I'm saying that if we have a column where the steel grade, the yield stress for the steel, or the allowable stress for the steel, is lower than the capacity for buckling, part A was controlled by buckling. Ooh. This problem is controlled by yielding. Does everybody see that? Does everybody see that because this dimension, which is the required dimension to hold the column up under buckling, is too small? If we use this allowed. Does that make sense? So the way that we handle part B is actually very easy. What we do is we say that sigma allowable which is 5 KSI, and just set it equal to P over A. So 5 KSI, or sorry, 4 KSI. I keep saying 5. 4 KSI just equal to 20 kips over A, which in this case is B squared. So B squared is 5 inches squared. B is the square root of 5, which that ends up being something like, B min is I think it's like 236, this is the square root of 5. Does that make sense? Is everybody understanding that? So my key takeaway I want for this lecture is this part right here. The idea that if we calculate the buckling load and figure out what the dimension buckling is going to cover, we find that the stress is higher than what the material can allow. And because the stress is higher than what the material can allow, we just use sigma equals P over A to determine the required B value. And that B value, I think that makes sense, right? Because this column was governed by axial stress, not by buckling. So it's make sense? All right. Dynamics.